So section 2.6 is implicit differentiation. So far everything we've done is explicit differentiation. We never really made that discernment. We'll see what the difference is here in a moment. This is a pretty handy technique for situations where x variables and y variables are tangled up in a relation of some sort, but we can't quite solve for y as a function of x. That's really what this first line is saying to us right here. So we can't find a representation of the form y equals f of x. And since most of our functions so far, and in a lot of the courses you probably had to this point, looked like this form, y equals some function of x, it might come as some bit of a surprise to realize that there are plenty of functions out there that aren't easily written as a function y equals f of x. In other words, can we solve for y in either of these two equations in a way that is, a satisfying expression to have? Well, the first one, yeah, to some degree, right? So maybe down below, we'll point out this. X squared plus y squared equals 4. I can solve for y in that, right? Y squared is equal to 4 minus x squared. And I want to solve for y as a function of x. So I take the square root of both sides, and that's 4 minus x squared. However, I took the square root. I introduced the square root here, so I need to put a plus or minus. Well, that's not really, I don't like a function or curve that does this, that has a plus or minus. For one thing, this actually isn't a function, right? What we knew from the beginning, as a matter of fact, was that the graph of this curve was a circle centered at the origin, 0, 0, with radius 2. Radius is the square root of 4 there. So we know a circle can't pass the vertical line test. So of course, it intersected in 2 points by this vertical line here, right in the middle of it. So of course, this is not even a function, but the relation nonetheless, the equation involved, we can find a way to find the derivative. In other words, there are clearly tangent lines to this circle. So we can find the slopes of these tangent lines with just such well, as a derivative, as implicit differentiation will give us, right? So, and we'll get to that shortly. So this is possible, but it's not great looking. I don't really like to deal with functions that look like that. On the other hand, if I look at this equation right here involving x and y, if I try to solve for y in this, it really gets messy, and there's not really any way to isolate a single y variable on one side of the equation and have the rest of this be only a function of x on the other side. So this equation or relation would be a situation where we'd be really happy to have the tools of implicit differentiation available to us in case we wanted to know what dy dx was, right? Dy dx, or the derivative of y with respect to x. Okay, so in this way, what we understand is that even though we can't write y as a function of x in something like this, we know that if we declare y to be the dependent variable and x the independent variable, as we typically will, we know that y in some way is some function of x that we can't really write down, but through its chain rule, we'll know, or through the chain rule, we'll know when we take a derivative of a function of y, like y cubed here, that we actually need to multiply by y prime, and we'll see why in just a moment. So that's really pretty much everything there is to implicit differentiation in terms of how to do it. So anyway, let's go for it, right? So I'm asked to find y prime, and we have that exact function we just looked at before. This again is the circle with radius 2, centered at the origin. So implicitly, what we know is that y is some function of x. And we did solve for it, plus or minus root 4 minus x squared. But that's not really a nice function to deal with since it has the plus or minus. So what we can do instead is get a reasonably useful derivative out of this without ever having to solve for y as this function of x. But what I understand is that y does depend on x in some way, right? That's what we're accepting in any one of these x and y equations here. So when we take the implicit derivative of something, we typically have an equation that we're looking at. We find the implicit derivative of this equation here. So in other words, we're going to take the derivative with respect to x of both sides. right? We're finding y prime, and it's just assumed then that if we're looking for y prime, we want the derivative of y with respect to, well, it must be with respect to x. That's the only other variable. Now, if they ask for find x prime here, which is a little bit unusual, uncommon, but still possible, then we would do something similar. It would be the derivative with respect to y. But we won't do that in these examples, and I don't think the textbook does either. So let's just get started with this. So I'll take the derivative with respect to x of both sides of this equation. So here's my derivative operator. So I'm going to take the derivative with respect to x. On the left-hand side, I have a sum rule. I'm going to take the derivative of x squared and then add to that the derivative of y squared. Well, the derivative of x squared is 2x. Okay, I'm going to add to that the derivative of y squared. I want to be careful here. I'll take my time with this in just a moment. Now, on the right-hand side, the derivative with respect to x of the constant 4 is just 0. The derivative of any constant is 0. So that's nice. This is simplified a little bit thanks to that. But now let's focus on this term right here. So there's actually a chain rule here, right? I don't know what f of x is necessarily. I could go looking for it. Most cases, it's not worth it. But I do know that if I take y's derivative, dy dx, well, that's f prime of x, or it's just some y prime, right? I know that this is some derivative here. And so once I get down to this, so my outer function is the squaring function here. I'm squaring this variable y, right? Inside this, the inner function is y, and y is some function of x. We just don't know what it is, but we can very happily call its derivative y prime. And that's a really neat thing about implicit differentiation, is this y prime pops out, and that's exactly what we're actually looking for. We want to solve for that y prime once it pops out. So this is what that looks like. So the next line below, we've taken the derivative of the outer function. So we have 2y. This is by the power rule on this function y squared. But now, instead of being done with this, we know that y is a function of x, right? So 2y, and then we have to take the derivative of the inner function y. So ddx of y. And that's where we can stop. This is just dy dx, the derivative of y with respect to x. And we know that character to be y prime pretty much always. So on the subsequent line, we write that as y prime down here. And now we can go about solving for y prime. Now we could have just left it as dy dx and solved for dy dx. We get the same thing. That's fine. Dy dx is equal to y prime, so that's perfectly fine. In doing so, though, we see that to solve for y prime, I need to subtract 2x from both sides, and then I'm going to divide by 2y, and that should get y prime all by itself. So what's happened here? Oh, looks like I divided by 2 on both sides. Okay, so that's fine as well. Right, we divide by 2. We still have a 0 on the right-hand side. And then now I subtract x from both sides. And then I divide by y. And I have that y prime is isolated by itself, and it's equal to negative x over y. It's very common for an implicit derivative, y prime, or dy dx, whatever we want to call it, to be a function of both x and y. And though it seems a little strange and maybe clunky to deal with, we'll see some examples where we can actually accomplish pretty much most of the things we ever wanted to with derivatives with this implicit derivative. Moreover, it'll be a useful tool when we look at related rates and other applied problems in some cases. So next up, we've got find y prime if this is the given relation, or of this function, or this equation here. So again, we have a constant on the right. We're going to take the derivative with respect to x of the left-hand side and the right-hand side. The derivative of that constant will be 0. So we've dispatched that term pretty quickly. Now we'll take the derivative of this sum of functions. And let's be careful, right? Put some steps together if you need it. The derivative of this sum is the sum of the derivatives for each of these terms that are added together. So I've clearly and carefully split that up. The next thing I realize is that, well, each of the functions I'm taking the derivative of is actually a product of functions. So I need a product rule in both cases. So for the first derivative I take, the first product rule looks like this. It's the derivative of this with respect to x. So derivative of x with respect to x is 1. derivative times the sine of y. So 1 times the sine of y. The product rule is still the product rule, no matter what this function or what variables are involved in here. Now, plus, from the product rule, the first function times the derivative of the second. First function is x. Second function is sine of y. And I've taken the derivative of sine of y here, and that's cosine of y. But I have an inner function y, which is implicitly a function of x. So the chain rule says take the derivative of it with respect to x. And that's dy dx or y prime. Similarly, we'll rehearse the one this term. So the derivative of this product is the derivative of the first term, which is d dx of y, or dy dx, which is y prime. We can write it as that, or dy dx, times the second function, and then plus the first function times the derivative of the second function. And then everything's equal to 0. We've already pointed that out. Now the task is this. We have y prime in two places here. We want to collect it together, or collect those terms together, and solve for that y prime. So the rest of this really is nothing more than algebra. A lot of times we don't get very clean and nice expressions. Nonetheless, they'll do the job that we need them to when the time comes. So expanding all this out, or I guess dropping these bars and writing the products more casually as we see here, we've got y prime, this x cosine y times y prime plus sine of x y prime. That's these two terms. The other two terms we've subtracted from both sides of the equation and effectively moved them over to the right-hand side as these negative terms. So we're pretty close to being done with this one. The last step we need to do is one of the next steps is to factor out y prime from both of these. That's why we collected these like terms. So now I have a y prime times each of these multiples as a sum here. If I distributed that y prime through this expression, I'd get back the line above. And so the last thing to do is divide by this binomial here. And so I have y prime is equal to the right-hand side with these negative functions over this multiple here. So this is our function y prime. It's the implicit derivative of y with respect to x. And sure, it involves x and y. It typically will. If it doesn't, then that means we probably didn't need implicit differentiation. Okay, so let's see what we can do with one of these derivatives. The next question asks us to find the equation of the tangent line to the curve x squared plus xy plus y squared equals 3. And this is at the point 1, 1. Okay, so this is a pretty non-trivial curve, right? It's not a circle because this x times y term is in there. So it's kind of hard to know what we're dealing with really here, right? But we don't have to know what we're dealing with. To find the tangent line of the curve at the point 1, 1, well, for one thing, we should be sure that 1, 1 is actually on the graph of this curve. So the way to do that is to plug in x equals 1 from the first coordinate and y equals 1 from the y coordinate into this equation and see if it's true. I have 1 squared plus 1 times 1 plus 1 squared. That's 1 added to itself 3 times. Of course, we get a 3. So that point is actually on the curve. They didn't ask us to check that. It's just nice to note that that is the case. What we have is most of what we need for a point slope equation of the line. The only thing we really need to know now is the slope of the tangent line to this curve at this point. How do you find the slope of a tangent line? Remember, that comes from the derivative y prime, or dy dx. So what we'll do in order to find dy dx is we'll take the derivative of both sides with respect to x of this equation, and that looks like the following. Derivative with respect to x of the left equals the derivative with respect to x of the right. The derivative of that 3 is a 0 because it's a constant. And on the right-hand side, I split this derivative over the 3 different functions that are in here. So the derivative with respect to x of x squared, that's the easy one. It's just 2x. X is an explicit function of x, right? Or x squared is an explicit function of x. So that's just 2x. For the middle term, I need a product rule. So I'll just write ddx of x times y, and we'll complete that in the next step. For y squared, Well, that's a pretty straightforward one. So I'm taking the derivative of y squared. The outer function is the squaring function. So its derivative is 2y to the first power, or 2y. We've already seen this one before. And then the chain rule says times y, times the inner function's derivative. And the inner function's derivative with respect to x is just dy dx, or y prime. So basically, anytime we take a derivative of a function of y like this, we take the derivative as usual and then put a product of y prime. Maybe you're seeing that and concluding that that's the rule for this, and that's just fine. So let's be careful with this middle term, right? This requires a product rule. So the derivative of the first function is 1 with respect to x times y. So there's that, plus the derivative, or plus the first function times the derivative of the second. The first function is x times the derivative of y. Well, that's just y prime. Okay, now we've got everything differentiated. We just need to solve for y prime. So again, I'll leave these two y prime terms on the left-hand side, and I'll subtract these other two terms to the right-hand side, as we see here in the next line. And then I'll factor out the multiples of y prime that are on the left-hand side. This is the x plus 2y from above. And I solve for y prime, and y prime is equal to this divided by this. So now we have our derivative y prime. How can we use this to find the slope of the tangent line? Usually we have an x value, y prime equals some f prime of x, and we plug in the x value and we get our slope. Well, in this case, we have an x and a y we need to plug in for. Well, they gave us a point, coordinate 1, 1. Just like we checked that this point was on the curve at the beginning, which wasn't necessary, but still nice to see that we can do. We plug in 1 for x, since that's the first coordinate of this point, and we plug in a 1 for y, since that's the second coordinate of this point, and then we calculate what y prime is for the point 1, 1. And that's going to be the slope of the line tangent to the point 1, 1 on this curve. So one way to note that, m is the slope of the tangent line at the point 1, 1 for the curve that represents the graph of this function. So this bar notation just says, okay, y prime, the derivative at the xy coordinate 1, 1. It's a way to read that. So instead of being y prime of x with parentheses, we can say, okay, y prime of the point, right? Y prime evaluated at this point, 1, 1. So x is 1, y is 1, and when we get done simplifying all of this, we see that we end up with m equals -1. So now we have our slope. Point slope form says y minus the y coordinate of 1 is equal to the slope, -1, times x minus the x coordinate of 1. And we end up with just this. And this is sufficient. Point slope form will do. They didn't ask for slope intercept form, but we could convert to that if we needed to. So yet another example, a little bit stranger than the ones we've done before, is the following. We're told that if g of x plus x sine of g of x is equal to x squared, find g prime of 0. So there's a sort of a whole thing going on here, right? So it looks like g of x is really kind of tangled up in this function of x, right? We can't solve for g of x on its own without making a mess, right? We can't get a single g of x on one side of the equation, or at least it doesn't appear that there's an easy way to do so. One hint I can give you is this for a shortcut. You could just say g of x is equal to y, right? And you could swap all these g of x's out and they would just be y's, and you could do everything as we've done above. But we could also, in turn, or as it's given to us, we could do the same implicit differentiation rules as we've done above. We don't know what g of x is, but it's clearly a function of x. Its derivative is g prime of x. So anytime we need to take its derivative, we'll just write g prime of x. So we attack this thing in the same way we've done all the other problems. We take the derivative with respect to x of both sides. What we're trying to get at is what g prime of 0 is. So maybe we should figure out what g prime of x is and then try to plug in 0 for x. Okay, so derivative of both sides. So ddx of the left-hand side is equal to ddx of the right-hand side. Well, the right-hand side's pretty easy. It's a power rule. 2x is the derivative of x squared. Okay, on the left-hand side, we have the derivative of a sum. So as always, we could split that up as the sum of the derivatives. Well, the sum of, or the derivative of g of x is just g prime of x. So here we've exercised that option, right? Now, plus the derivative of this function. Well, this is a product function. It also is the product of this function and then a composite function. So we're going to have to be somewhat careful with this. So for this product rule, we use the derivative of this function times this one. So that's 1 times sine of g of x. Okay, and then plus this function times the derivative of this one. So there's x times the derivative of sine is cosine of g of x times the derivative of the inner function. The derivative of g of x is g prime of x. So now we've carefully navigated that. Like I said, if that was confusing or you don't like it, you could always swap the g of x for a y and work in that way. And then remember that y is equal to g of x. So now I realize that g prime of x and g prime of x here occur in a couple places. So I'm going to group those terms and factor them out. So g prime of x corresponds to this 1 here, because g prime of x times 1 gives me this term. And then g prime of x times this term gives me this term. So in that way, I have g prime of x times 1 plus x cosine of g of x. Okay, what did I do with the term that doesn't involve g prime of x? I moved it over to the right-hand side. Now my last move is to divide both sides by this binomial, so I solve for g prime of x. And in doing so, I've got the right-hand side divided by this multiple here. And I know what g prime of x is. Now I want to know what g prime of 0 is. So now I'm all set to do that. I know g prime of x. I can plug 0 in for x. For all of these, it's going to be a little tricky to figure out what some of this is, but let's just go for it, right? So 2 times 0 is 0. Plugging in x equals 0. Then I have sine of g of 0. Okay, so that's problematic. I'm just going to write it as g of 0. I don't know what that is yet, but maybe we can figure it out. The denominator, 1 plus x times cosine of g of x. Well, 1 plus 0 times cosine of g of 0. Well, I don't have to figure out g of 0 here because 0 times cosine of g of 0 is just 0. So this is a 1 in the denominator. And what I'm left with is that g prime of 0 is just equal to negative sine of g of 0. So the term that survives is all that's divided by 1. It's 0 minus sine of g of 0 in the numerator. What is g of 0? How might I find that? Well, the only thing I can try is maybe I go back up here and just see what happens. If x is equal to 0, maybe I can solve for this as a g of 0. Well, g of 0, when x is 0, this is 0. So all this expression is going to be 0. And then 0 squared is 0. So g of 0 plus 0 equals 0. And I think that's written down at the bottom of the page. Let's have a look at that. Yep. It's all right here. Plugging in x equals 0 to the top, we get that g of 0 is equal to 0. So in the very end, we did all that work to find out that, well, g of 0 is 0, and then sine of 0 is 0. So g prime of 0 all along was just 0. There we go. Now we can take multiple derivatives implicitly. Okay, so we can find, just like we can find y prime, we can find y double prime. So let's see at least one example of that now. So we are asked to find the first and then the second derivative of y for the equation root x plus root y equals 1. So I change these to fractional powers to make my differentiation easier. And I take the derivative of both sides. The derivative of the right-hand side with respect to x is going to be 0. We've seen that multiple times now. Now the derivative of the sum is the sum of the derivatives. The derivative of x to the 1/2 is 1/2 x to the negative 1/2. So that's this term here. And the derivative of y to the 1/2 is 1/2 y to the negative 1/2. And don't forget the chain rule or the rule of implicit differentiation that this is times y prime. That implicit function of x. This is dy dx, right? The operator moves through y to the 1/2 and it hits y And it doesn't just differentiate to 1, it differentiates to dy dx, or y prime, just as it always has. Okay, so now multiply both sides by 2 to get rid of those pesky 1/2. So those are gone, and we have this line. We want to solve for y prime. So I'll subtract x to the negative 1/2 from both sides. Then I'll divide by y to the negative 1/2. And I end up with this expression for y prime. And since I know I want to take another derivative of this, I'd rather not it be a quotient. So what I'll do is I'll move this y to the negative 1/2. It's kind of handy. It's got a negative power in it anyway. I'll move it up to the numerator, up to the floor. Well, and when I do that, I change its sign, its exponent sign, from negative to positive. That's actually pretty convenient. It's a nicer expression for this. So now I know that y prime is the product of negative x to the negative 1/2 and y to the 1/2. Now I'm in a good place. I think this is a manageable function or manageable expression to try to find a second derivative of. Okay, and this is where it's going to get a little weirder. So let's see what happens when I do that. I'm going to take the derivative of both sides of this equation, because on the left-hand side, y prime is going to become y double prime. And that's great. That's something I'm looking for. So on the left-hand side, we have y prime. On the right-hand side, I take the derivative with respect to x of this function. And that's going to be as it normally looks, right? I'm going to have d dx of this function. And it's a product rule. So I'll do the derivative of the first times the second function. So that's going to be 1/2, positive 1/2 x to the negative 3/2. Double negative of 1/2 will give us a positive 1/2 times y to the 1/2, right? This function is just there as itself. And then it's this function times the derivative of this function. Right? So plus this function times the derivative of the second one. Well, the derivative of y to the 1/2 is 1/2 y to the negative 1/2, and then times y prime. It's the implicit derivative of y there. Right? Well, that chain rule bumping up against y. So this looks good. Everything looked great. And maybe the only thing that concerns us is we're looking for y double prime. And along the way, we got a y prime thrown in there. Maybe that is a little bit disconcerting. That kind of makes a mess out of this potentially. But really, it doesn't, because we know what y prime is from above. And we want all of this function to be in terms of x and y. Just like this one is in terms of x and y double prime, we'd like to see it in terms of x and y as well. So the only thing we need to do is substitute that y prime out with what we already know it to be. So in two ways we use the first derivative. We use it because we're going to take the derivative of the first derivative to get the second derivative. And anytime a y prime pops out, we can substitute that first derivative for that. Similarly, for a third or fourth derivative, we could go back however many levels we need to other previous derivatives that were calculated and keep substituting those expressions in. Now, y double prime, what is this? Really, the only thing we've done here is we've written all of this down again, maybe cleaned up some parentheses, and then swapped out y prime for this term. It looks like there's some simplifications that are done here. Y to the 1/2 times y to the negative 1/2 is going to be y to the 0, which is 1. See that happening here. And then this product is going to be x to the negative 1 when we add those two negative 1/2s together. This coefficient of negative 1/2 is multiplied by this negative sign, so this becomes a positive 1/2 here. And it looks like this term stays the same. Yep, that's true. So when we're all done with this, our second derivative looks like this. Really, in the end, it's just a bit of algebra to clean it all up. So there it is. And I think that's about as complicated as our implicit differentiation gets, right? Taking the second derivative, just note, or a higher order derivative, a derivative more than the first one. Just note that y prime or y double prime, if you're finding y triple prime, might show up, and you can use previous information to swap it out. I think the harder work here is to clean up all the algebra when you're done with this. So that's it for implicit differentiation.